Good afternoon. My name is Paolo Comini. I am a structural engineer and I work for the company Seismic 360. Today I will talk to you about the use of wall analysis in the assessment of buildings with flexible floors. So firstly, I will quickly introduce who is and what does the company I work for. Seismic 360 is a consulting company active in the field of seismic engineering. We assist both engineers and engineering firms in the seismic and structural analysis of the new and existing buildings. We have been involved in various projects in residential, public, and also industrial sectors, both in Italy and abroad, as Andrea mentioned before. And this includes a major campaign to assess the seismic vulnerability of residential buildings in the Groningen region in the Netherlands, in which we participated together with our Dutch partner, Econstruct. From 2018, we have analyzed about, just one moment, about 300 buildings in the Groningen region. And this campaign will serve as the background for my presentation today, which is based on our daily based professional activity. The issue of earthquakes in the Groningen region is linked to the gas extraction. The gas field was discovered in 1959 and is the largest in the Western Europe in terms of size. The problem is that 90% of the buildings in the region are built with masonry and were not designed to withstand seismic forces. So for this reason, since 2014, alongside the reduction in gas extraction, a campaign who assessed the seismic vulnerability of buildings in the region has been started, in order to identify any critical issues and reinforcing buildings where necessary. The seismic vulnerability assessment is carried out. Carried out in accordance with the guidelines NPR. These guidelines have undergone several modifications and updates over the years, leading to significant differences in the definition of the seismic capacity of buildings. These guidelines are available in Tremuri among the list of national codes that can be applied in the calculation. The NPR guidelines differ quite significantly from the codes we are accustomed to, such as, for example, the Eurocode 8. In the bottom box of the slide, you can see some peculiar characteristic aspect of this guideline. The newer NPR guidelines push the structural capacity much further than, for example, Eurocode 8, as you can see from these values. We have talked about the capacity. Now let's discuss about the demand. The seismic input is obtained from what is called NPR web tool, which is essentially an internet accessible database. By entering the geographical coordinates or the address of the building, it provides the elastic spectrum and also other data that can be useful in structural analysis. Due to the progressive reduction in gas extraction, the seismic inputs has significantly decreased over the years, which has had a major impact on defining the demand. At the beginning of the assessment campaign, so in 2018, for example, most buildings required rather major retrofits. In particular, diaphragms were being retrofitted by stiffening them in any case. And so for this reason, there was no emphasis on analyzing them with their real flexibility. With the various updates of both the guidelines and the seismic input, the trend changed and the need arose to analyze building using the real stiffness of the floor diaphragms. So single wall analysis became very important. Also in this case, in the bottom of the slide, I present some information regarding the Dutch case. So the return period, the PGA, the maximum PGA. The buildings that my colleagues and I have come across over the years mainly fall into three typologies. So detached houses, terrace houses, and barn houses. Regarding walls type, Dutch buildings have much thinner walls compared to those we are accustomed in seismic countries, like for example Italy. The majority of the structural walls have a thickness of around 100 millimeters and are primarily made of two materials, so the clay and the calcium silicate. The use of the calcium silicate began around the 1960s. Thicker single wall of 210 millimeters are typical for perimeter walls in buildings from the early 1900s, while newer buildings have cavity walls on the perimeter. Let's focus now on the floor diaphragms. We can have three major structural typologies. So the first one is timber floors, timber diaphragms, constructed with either a simple boarding, so simple blacking, or one or two panels of OSB, oriented strand boards. These three solutions have increasing stiffness. The second structural typologies are hollow core slabs, which can be of two types. The first one is a very typical Dutch typical components that are the neobo slabs, which are hollow core slabs made with perforated brick units connected with the cement mortar. These were commonly used in construction from the 50s to early 80s. And usually they cannot be considered as rigid. The second typology of hollow core slabs are the press-stressed hollow core slabs. These are typically in construction from the 80s onwards and often have a collaborating topping sufficient to be considered as rigid. Lastly, we have the cast-in-place reinforced concrete slabs that can be considered as infinitely rigid. The diaphragms play a crucial role in the seismic response of buildings, and two limit conditions can be considered. So the first one is the limit condition of infinitely rigid diaphragms. These are rigid diaphragms in their plane that do not experience shear deformation. When dealing with such a diaphragm, so for example a reinforced concrete slab, a cast in situ reinforced concrete slab, global analyses are the most appropriate. The second limit condition are the infinitely flexible diaphragms. These diaphragms have a significant distortion in their plane, and they are unable to transfer horizontal forces between parallel and transverse walls. So in this condition, each wall responds individually, and the most representative analysis is or are the single wall analysis. Between these two limit conditions, there are the intermediate all the intermediate cases. Let's consider this very simple building consisting of two walls for each direction. The mass can be concentrated at the top of each wall. Therefore, for a specific direction, we have the stiffnesses of the two walls and the stiffness of the diaphragm. When I say stiffness, I also mean strength, as in nonlinear analysis, such as in a pushover analysis. The two are interconnected because in the nonlinear range, initial stiffness is no longer a good parameter. If the stiffness of the diaphragm, so the green one, is much lower than that of the walls, especially the more flexible one, so the red one, K-flex. In that case, each wall is responsible for the mass concentrated at its top. Therefore, in this case, the most representative analysis type is the single wall analysis. On the other hand, if the diaphragm is much stiffer than the walls, in that case, global analysis can be used because the diaphragm can couple the behavior of the two walls, and torsional effects are also possible. In reality, actual buildings lie somewhere between these two scenarios. Our approach is to consider the ratio between the magnitude of the stiffnesses involved. So if the diaphragm, so the green one, has a stiffness in the same order of magnitude as that of the walls, that is, if the K diaphragm is at least 10% of the stiffness of the weakest wall, so the red one, in this case, we perform global analysis. In the other one, single wall. So now the problem is how to evaluate the stiffnesses. Regarding the stiffness of the diaphragms, the NPR guidelines provide tabulated values of second stiffness for different types of floor systems at various drift levels. Specifically, they provide values at two drift levels, 0.1% and 1%. Not all types of floor system are included in the tables. So for those not listed, reference can be made to specific scientific literature. The biggest issue is how to evaluate the flexibility or the stiffness of the walls. One might think of considering the elastic stiffness of the wall piers, which, however, is not representative of the nonlinear behavior of the masonry, and at the same time turns out to be a very high stiffness that almost always forces a single wall analysis in the case of timber floors or semi-rigid floors. Therefore, we devised a more, how to say, non-linear or practical approach. And I want to underline that what I show you is our approach, and I underline the word our. It is not proposed in any official document. It is not. It is just a formulation we came up with to give us a rule in applying one type of analysis or the other. So, step one, since building a 3D model of the structure is required for conducting a single wall analysis in Tremori, we propose using this model to perform a global pushover analysis with rigid diaphragms. Step two, the shear force at the base of the most flexible wall is evaluated at a specific displacement delta, which I will define shortly. Step three, the stiffness is calculated as the force divided by displacement delta. And finally, step four, this stiffness is compared to the diaphragm stiffness. Sorry, I don't know why. The displacement delta we have chosen in the displacement for the displacement, which correspond to a 0.1% in plane shear drift for the diaphragm floor. We have selected this default value because it often falls within the nonlinear range that is typically around 4 to 6 millimeters, while still being far from the ultimate condition. Now I present you a very simple case study, a building located in the city of Uskert, or village of Uskert, in the northern part of the Groningen region. It consists of a ground floor and a first floor located under a gable roof. Regarding the ground floor, all the walls are made of clay brick masonry, except for the wall indicated in green, which is made of timber. The floor separating the ground floor from the first floor is made of timber and consists of timber beams arranged in the y direction with a spacing of around 1 meter, topped with timber planks. This type of diaphragm can be considered quite flexible. So we apply our procedure. So step one, firstly, we perform a global analysis with a rigid diaphragm in thermoid. Here are the results. Everything is verified, green color. Now, let's consider the walls arranged in the x direction, so the direction perpendicular to the floor joists. We divide the floor into two diaphragm fields, diaphragm 1, the blue one, and diaphragm 2, the red one. We have to consider their dimension in order to calculate the displacement relative to the drift of the 0.1%, for which we are going to evaluate the shear force at the base in each wall. The relative displacement for a drift of 0.1% in the two diaphragm fields are, for diaphragm 1, approximately 5.5 millimeters. For diaphragm 2, approximately 2.25 millimeters. Now, let's refer to an analysis in the x direction, such as, for example, the pushover number 3 in the negative direction without eccentricity. At this point, for each wall, we can query the results from Tremori and extract the shear values of each element of the wall in the x direction at the target displacement that we have calculated. In this slide, I present an example for the wall P1. This wall is connected only to the diaphragm field number 1. So the displacement at which we evaluate the shear is 5.45 millimeters. So the closest pushover analysis step to the target displacement for wall P1 is at a displacement of 5.48 millimeter. We can extract the tabulated values of all the elements belonging to that wall, and the total base shear for the wall, for this wall P1, will be the sum of the shear values at the base of these elements. We follow the same procedure for all the three walls in the x direction and that we are analyzing, and the results obtained are shown in this slide. We can see that the wall P1, P2, and P3 have base shear values approximately equal to 28 kilonewton, 66 kilonewton, and 48 kilonewton, respectively. By knowing the base shear and the associated displacement at which the base shear was calculated or evaluated, we can now compute the stiffness of all the three walls, denoted as KP1, 2, and 3. It can be observed that the wall P1 is the most flexible. We evaluate now the stiffness of diaphragm using the approach proposed by Brignon et al., which depends on the three contributions, so flexural contribution of the planks, the shear one, and the slip lane contribution of the nails. Now, knowing the stiffnesses of the walls and the diaphragm, we can compare them and see if the diaphragm stiffnesses are in the same order of magnitude as the wall stiffnesses. As you can see, the ratio between the two stiffnesses is always less than 10%. Therefore, we can conclude that the diaphragm stiffness or the diaphragm stiffnesses are not in the same order of magnitude as the wall stiffnesses. So according to our, and underline our, practical approach, we should perform single wall analysis. Out of pure curiosity, I performed 2 analyses, one for each direction on the global model, but this time I included the actual stiffness of the floors to observe the behavior. As you can see, the shear deformation of the diaphragm is significantly pronounced, and in the X direction, the global analysis transforms into a pseudo single wall analysis, more or less, with no meaningful outcome. At this point, we will use the single wall analysis tool provided by Tremori, so we can compare the results. In this slide, I show you the comparison between the global analysis performed on a model with rigid diaphragms, the yellow one, and the single wall analysis. As you can see, all the global analyses were verified, as indicated by the green color. However, the single wall analysis for the wall P5 resulted in a red color, indicating that it did not meet the verification. They did not meet the verification criteria. Similarly, in this slide, I have provided a comparison between the global analysis conducted on the model with flexible floors and the single wall analysis. And once again, all the global analyses were verified as indicated by the green color. These are the results, the critical pushover for the wall P5, and we can see that the ultimate displacement is reached at a drift of 1.3%, which is higher than the value prescribed by the Eurocode, which is equal to 1.06%. In conclusion, diaphragm stiffness is a key parameter in assessing the seismic behavior of buildings. And for this reason, it is important to evaluate it as best as possible. Through the procedure presented today, we have established a criterion for determining when to employ a global or single wall analysis. By comparing the in-plane stiffnesses of masonry walls and diaphragms, we can make informed decisions about the appropriate analysis approach. The Tremori software allows the user to define the in-plane stiffness of a diaphragm, and in case the diaphragm is not sufficiently rigid, also allows the user to perform single wall analysis. Finally, it is important to note that performing global analysis on a structure with highly flexible diaphragms may yield misleading results, as I showed before. Therefore, it is crucial to consider the relative stiffnesses of the components involved to ensure accurate and representative analysis outcomes. So thank you to everyone, and for additional information you can find here my contacts and also the email address of the company and the website of Sismic Data 160. Thank you.